So to continue our study of calculus, in particular differentiation, we are forced to know the differentiation of several numbers. For example, e to the x powered, 1 over x, and a to the x powered. So in this video, I'm going to state the rule for these differentiations and also prove them. Because honestly, I always believe that knowing how to prove a rule is always better than just memorizing it. Okay, so start with the first rule we're going to differentiate to prove, which is the derivative of e to the x powered is equal to e to the x powered itself. So the first thing we do is again restating the definition of limits, the definition of derivatives, okay? Because again, this definition is gonna help us a lot improving the rule once again. And the more proving in calculus you do, the more you realize how important this rule is. Basically, every time this rule comes in handy. So let's just box this rule. Now, from this rule, we know that the derivative of e to the x powered is equal to limit, as h approaches 0, of e to the x plus h powered minus e to the x powered over h. Okay. Now, factoring out e of x from the expression from the limit, okay, let's put e of x right here. We're left with e to the h powered minus 1 on the numerator, and h on the denominator. So now we just need to deal with this limit right here. Okay, so how do we deal with this limit? We are going to use something called the Maclaurin series, or more rigorous, the Taylor series that expands at x equals 0. This is a much more advanced study of calculus, which we are going to cover in later videos of calculus. But for the sake of proving this rule, we are just going to use it right now. So the Maclaurin series expansion for e to the h, which we're going to represent, is equal to summing up from n equals 0 to infinity of h to the nth powered divided by n factorial, which, let's list some of the values. So we start with 1 plus h squared divided by 2 factorial plus blah 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 plus h to the nth power divided by n factorial. So now basically we can just represent e to the h using this expression here, and we can substitute this into our expression. So now what we get is substituting this expression we have here, 1 plus h squared divided by 2 factorial plus blah 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 plus hn divided by n factorial minus 1 divided by h. Okay, so we can cancel out the 1's here, and we can cancel out the h's here. Okay, divided by h. So this is going to be 1. This is going to be h to the n minus 1 powered. Okay, so simplifying this a bit, we get ex times limit as h approaches 0 of h. Sorry, I think this is 1 here, because divided by h divided by h is 1. Okay, so we're left with 1 plus h divided by 2 factorial plus blah 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 plus hn minus 1 powered divided by n factorial. Now, notice that h is approaching 0. So basically, we can state that every single h is equal to 0. So every single term that includes h will be equal to 0. So we can basically cancel out all of this 0 terms. So what we're left with is e of x, because we're left with a single 1 here. And 1 times e of x is e of x. So we have successfully proven the first rule.